very good morning, good afternoon and good evening to all my dear friends, participants and students. Welcome to this course, title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, by this time these three words would have almost gone and settled down in your memory permanently. As you are aware, I repeat it, there are three main topics, broad topics we are covering in this course of 30 hours spread over 60 lectures, 12 weeks. The first topic is forecasting, second one is regression and third one is time series. And we are, as you can recollect, I did mention in the last two lectures, we are in the midst of the fag end of this regression models. And there are a few important topics to cover and we will then move into time series. This is week number 9, lecture number 43. What is the coverage? Planned coverage. I should basically say planned coverage because as the course progresses, as the lectures proceeds, there are many discussions which takes place as I talk, considering all of you are sitting at the other side of the camera and listening to me. So, depending on the flow and the speed, generally the coverage gets a little bit more exhaustive and more detailed. So, whatever coverage I write, as I mentioned, in the final slides they may be changed. So, when you see the lecture and the videos and refer to the PPT slides, it would make much better sense. So, the coverage part would basically be reduced depending on the actual progress of the course as we proceed. So, the coverage for this lecture is balance loss function, considering the balance is being made between two loss function, which is squared error loss and LINEX. So, you are combining them in some proportions. We have discussed that in the last lecture in details, and also consider other loss functions pictorially, not go into much theoretical details and explain that in qualitative sense. So, if you remember in the last lecture, we were discussing in quite detail that what happens for the balance loss function if the losses are a combination of squared error and LINEX, which is the environment, and the estimate which you are trying to utilize for the balance loss function to be fruitful in further prediction was for model 1 and 2 it was squared error loss, and model 3 it was LINEX, and we will continue the discussion in the same line. So, in model 4 we are considering the squared error loss being the component for precision of estimation based on the fact that I want to find out beta squared error, because it's beta minus beta hat transpose into beta hat, which is squared because it is in the vector notation. And the second part where we are giving the weightages of 1 minus lambda, in the squared error the weightage was lambda, and in the second part it would be 1 minus lambda. I will use a different color, and the loss is LINEX, and its goodness of fit corresponding to the fact that one wants to find out theta. Now, as I said, in model 1 and 2 we consider the estimate to be squared error, in model 3 the estimate to be LINEX, and in the same continuation, the same logic, we are considering the estimate in the fourth model also to be LINEX, and it is pointed out here. I am marking it in green, and we have double checked, triple checked in the last lecture, that is theta LINEX is also scalar, considering the dimension of L transpose, X transpose X, X transpose and Y, and the corresponding things. And the risk comes out to be, there are two paths. The part 1 is corresponding to lambda, and the part 1 is part 2 is 1 minus lambda. So, let us concentrate on part 2, which is the weightages is 1 minus lambda. If you see here, I will use the red color. 1 minus lambda is scalar, a square, sigma square are scalars, we know what A is, and this part L transpose into X transpose X inverse in L is a scalar. We have shown that time and again throughout the discussion. But the first component which is being multiplied by lambda, it is not a scalar because it is X transpose X inverse in both the terms. So, as you keep changing the values depending on what you want to find for theta, this, if you remember, in model 2 also I said, this model 2 risk and model 4 risk along with model 1 and 3, obviously they are very interesting use in the area of sampling, which I said is not under the purview of our discussion. Considering the scalar form of the risk for model 1 and 3, we will concentrate on trying to show how does the risk behave on two facts. Obviously, we will consider our multiple linear regression model with X transpose X being given and L being given. We will change, and sigma square is given, we will change the value of A and lambda to pan out and see how the overall risk based on model 1 and 3 changes for different values of A and different values of lambda. So, where the calculation has been done, I will show, and what is the output, I will also show. Where the calculation has been done is in the Excel file, and the final output will be shown in the PPT slides, which I am now displaying. So, I will now go back to the Excel sheet to show, or Excel file to show where the information set is, because it will be shared with you. So, I will switch to the Excel file. So, if you go to the Excel file under regression, obviously regression will be given as a separate file. So, that is what I said. For my ease, I have kept all the sheets in the same single Excel file. First one being distribution, second one is forecasting. We have utilized forecasting data, Excel sheet time and again, and they were corroborated with detailed examples which are there in the PPT slides. In the regression one, there is a title balance loss function, and under that I have model 1, which you see here. You have model 2, then you have model 3, and finally you have model 4, and they are corresponding to the 4 models we have considered. The sigma square value, which based on one data set, is considered and calculated to be 52 into 10 to the power minus 4, which is 0.0052, and the sigma square is fixed for model 1, 2, 3 and 4. This X transpose X inverse is not required, at least it would be, it is required for model 2 and model 4, but I am not writing it because the calculations are not shown here. I would only like to concentrate on the simplest part. The third part which is required is that L transpose into X transpose X inverse into L, and that is value is 0.0036 as calculated, and it is utilized same value for all the 4 models. The L value is 1 as given for model 1, 2, 3, 4 always, you see this, they are same. The beta hat values for model 1, 2, 3, 4 are as given. So, there are corresponding to beta 1, beta 2, beta 3, beta 4, because there is x1, x2, x3, x4. I have not utilized beta naught. You can utilize beta naught, but I have not utilized this here. So, beta 1 value or beta 1 hat value, to be more precise, is 17 into 10 to the power minus 4. Beta 2 value is 14 into 10 to the power minus 4. Beta 3 hat value is 0.9456, and beta 3 value is 0.9456 and beta 4 value hat value is minus 7 into 10 to the power minus 3. And if you see, the values are same for model 2, also model 3 and also model 4. So, all 4 models use the same data set, and based on the fact that L is 1 and similarly beta hat values are given, which I am just highlighting. If you check, the theta hat value comes out to be 0.9417, again same for model 2, model 3, model 4. Now, what do? I take all values of A. So, A is given in column V here. I am only concentrating on model 1, and the same repetition would be done for 2, 3, 4, but obviously for 2 and 4, considering the scalar factor, scale value is not there, is a matrix, hence we are omitting for the time being, because this is not under the purview of this course. So, all values of A starting from minus 1.25, then it goes to minus 1.15, and if you see the last value is plus 1.25. So, all the values are taken with an increment values of 0.1. So, I am panning out all the values of A. Now, if I go to lambda, I have taken the values of lambda as 0. So, weightages of lambda. Then the next value of lambda I am taking is 0.25, then I take a value of 0.5, then I take a value of 0.75, and the last value of lambda I take as 1. So, as the values of lambdas are, so would the change happen for 1 minus lambda, that is the weightages. And if you remember the weightages, lambda was the weight given to the concept of precision of estimation, and 1 minus lambda was the weight given to the goodness of fit. And for all our 4 models, squared error loss was used in the first part, LINEX loss was used in the second part. But the formulation of the LINEX, what you want to find, formulation of the squared error loss, what you want to find, would change from model to model. Environment remains same, squared error and LINEX, but the nitty-gritty is based on it, what you want to find out, whether it is related to y, whether it is related to beta or theta, would keep changing. And so would the estimate also change, what you are trying to utilize as an estimate given the environment. And for model 1 and 2, it is the squared error loss estimate for beta, and for model 3 and 4, it is LINEX loss estimate. And if I go back, I have discussed about what I have taken in lambda, and here I find out the risk. The risk value which you find out, the formula is given. If you check here, everything is given. This formula is for model 1, is the one which I have utilized in model 1 in the last lecture, the risk. Similarly, when I go to model 2, it is written as NA, because these being matrix I am not doing the calculation, and I have marked it. This part is marked, that dimension is a problem, hence I am basically skipping it. Similarly, same concept of dimensionality is given in model 4 also. And if I take model 3, again the same thing, A values pan out from minus 1.25 to plus 1.25, lambda values go from 0, 0.25, 0.5, 0.75, 1 for all the 4 models, and risk 3 values is given. The equation and all these things what you find out here, which I have highlighted, is exactly what we can find out in the PPT slide for model 3. And similarly, the model 4 can also be used, which we were discussing. Now, let me go back to the PPT slides. So, based on that, when I go back, now I will give you the results. So, what do I take for the starting? I take the value of L as 1111, beta LINEX squared error I know, theta squared error I know, theta LINEX also I know, and from here I can find out beta, the formula and the value of beta LINEX. So, technically this should be beta LINEX, my apologies. This is this is right, there is no error, my mistake. This is squared error. Actually, I should have written, in order to make it more explicit, that this part theta LINEX is equal to L transpose beta LINEX is equal to L transpose beta squared error minus this term, which is A sigma square by 2 into L transpose X transpose X inverse L and that. So, generally, and I will mark it here, I should change the colors to make it much more evident. Let me mark it here. Wait. This I will mark as, let it be blue, because the color change would happen somewhere else. Just give me 1 minute. So, let it be theta LINEX. What I would change is this. One part I will mark in red. This is beta LINEX, and this would be, I will use the green color, yes. Yes, now see it. So, L transpose beta LINEX is equal to L transpose beta squared error minus a term. So, the question is that I know beta squared error, fantastic, which is given in the second bullet point. I have not written any formula for beta LINEX. We do not need the formula, we only need the value, because if you keep changing L, so if in case you have L as 1 0 0 0, we have seen that, I will come, then in that case actual beta found out LINEX would actually be beta hat LINEX, and depending on where you place 1, you can find out all those values, and we did do that. So, sigma square value is taken as I mentioned, 52 into 10 to the power minus 4, and this term we have taken from the calculation as 36 into 10 to the power minus 4, n is 75 and p is 4, as it should be. P is 4 because there are 4 values of L. Once I utilize this and use that formulas of model 1, 2, 3, 4, obviously model 1 and 3 is being utilized, and that Excel sheet, if I put that for different values of A, different values of lambda, I get this table, and there is a detailed graph also. So, let us see, from exactly taken from the Excel sheet. The first concept, as I change lambda and keep it fixed at 0, A changing from minus 1.25, minus 0.75, 0 plus 0.75 and plus 1.75, the risk 1 model is always 0. For risk 3, because I am comparing risk 1 and 3, the values change from minus 1.25, it is 8 into 10 to the power minus 4, goes down to 3 into 10 to the power minus 4 for A is minus 0.75, which is in column 2, for a value of 0, when A is 0, it is 0, and then for values of A as plus 0.75 in the fourth column, when I am putting 2 tick marks, and in the last column, row, sorry, my mistake, in the fourth row for values of A is plus 0.75 and for the last row plus 1.25, I find out the risk of model 1 remains 0, as I mentioned. For model 3, it is 3 into 10 to the power minus 4 and 8 into 10 to the power minus 4. That means it falls and then increases. And you will very interestingly see later the graph which you get is all the well known graphs which you have seen. Its behavior is exactly the same what you have encountered in many of the examples. Similarly, when I go to the values of A remain same, minus 1.25, minus 0.75 and goes to plus 1.25, lambda is now increased to 0.25. That means, I am giving a weightage of 25% to squared error component and 75% to the LINEX component. Now, if I get that, risk 1 remains exactly the same, constant, it is not no more 0, it is constant, which is 0.0923, and the behavior of risk for model 3 happens like this. It starts at 0.0931, which is row 1 value, last value, falls down to 0.926, again falls down to at a value of A 0 to the least value, least you will see later on as you see check with the graph, and then keeps increasing in the same quantum. For the second last row, which is for A is equal to plus 0.75, it is 0.0926 and last value is 0.0931 for A plus 1.25. I repeat this, for values of A being fixed, lambda now being 50%, squared error loss same, LINEX loss same weightages. Risk model 1 has increased from 0.09, it has increased to 0.1846, 0.09 and only read the 2 places of decimal. And risk for model 3 again has a very nice pattern. From a high value for 0.1854, it decreases to the least value of 0 is 0.1838, then again increases in the same quantum of nice smooth behavior. Then when I give 75% weightages to LINEX loss and 25% weightages, no 75% weightages to squared error and 25% weightages to LINEX loss with the same sets of values of A as given in column 2, risk for model 1 has increased. It is now constant obviously, but is increased to 0.2769, all the values being same, and model 3 values has also increased, but the pattern of decreasing then increasing remains same. That means, it decreases from 0.2777 to 0.2772 and then again falls to 0.2767 for a value of A as 0 and then keeps increasing in the same quantum as it had come down. And finally, when I take the value of lambda as 1, which means all weightages on squared error, 0 weightages given on this concept of LINEX loss, A values being same from minus 1.25 and goes to plus 1.25 in the quantum as given. So, risk for model 1 has now further increased, but again constant for all the values, it is 0.3692 and the value for model 3, it basically decreases from starting from a value of 0.3699 to 0.3695, then goes to the least value of the 0.3688 for A value as 0, again increases in the same quantum. Now, when I plot the graph, I will come to the Excel sheet. When I plot the graph, this is a very interesting part. This is the graph which you see for model 1 and model 3 for all the values starting from A from minus 1.25 to plus A 1.25 and lambda value being 0.5, equal weightage to LINEX and squared error. And the violet line is the line which is constant for all the values of risk. For risk 1, it is constant. That may change as you change the combination of A and lambda, but once you fix the value of lambda, it remains fixed. But for the values of A changing, you can have a change, which we will see within few minutes. And the value of the risk is so nicely depicted like a squared error loss. Even though you may be asking that we are using concept of LINEX loss, but remember, you are taking in a combination of LINEX loss and squared error loss, and for the value of a, because it becomes a square or a, hence the behavior of this curve for the risk is coming from the fact of the behavior of A, because other concepts like the values of sigma squared is not changing, L is not changing, X transpose is not changing, X is not changing. Only you can play with the values of lambda in A, and the values of lambda A and A having an effect, because lambda would basically be the weightages and A would basically give you the concept of the LINEX loss component of the parameters. If you remember, B and A, B was basically the scaling factor and A was the other factor based on which we considered. Now, let us go to the Excel sheet. So, here it is. So, if I see, so if I plot, I will take the values of A, lambda and risk and check how it behaves. Now, this is the interesting part. If I take the lambda value, now if we take the risk, these are the risk corresponding to the dot points which you see. Let me join them in the sense so the lambda value is increasing with a step function which is not at all required to be plotted, we know. I would like to plot these and I will show you. This is not the one fact which you want. I will take this value first. For lambda being 0 and A changing from minus 1.25 to plus 1.25, we have already seen, but I will plot it as required. So, this is the plot which you have already seen. Lambda is not required, so we can remove it, but I will show it how it. So, if I move it down, I am taking a value of the first set. So, I move it, yes. So, I go back, I move it here, this is the value, yes. So, if we see here for the second set values, the values of risk 1 is now constant. It was 0, now it is constant, and then again it will change. So, if I check the values, so the values of risk 1 always remains constant. We have seen it. What happens to the values of model 3? Yes. So, model 3 if I take, so these are risk values which I will take. Now, you may be thinking the risk values are only 4 decimal places and still we are getting a graph quadratic, because I have only taken 4 places of decimal. So, if I go here to model, I will just clarify, just I have to basically hold these values, yes. If I come to, so this is the value which I will get when the case of model 3, same quadratic, but the quantum of the risks which you have seen in the values you have what change. So, from this you can get all the different calculations which are done, there should not be any confusion. Now, let me come back to the last part of the discussion, which is other type of loss function. This is very brief. So, other type of loss functions can be the linear loss function, which can be utilized. We have not utilized in the multiple linear regression. The only problem is, number one, there are two parts problem which should be remembered. The first problem is, if I go in and around the value of 0 here, then the concept of continuity and limit concept are a problem, if you remember, for mod functions. So, hence for values of delta being very small, it may be difficult to utilize theoretically, number one. Number two is that as it is of equal quantum on the right hand side and left hand side, that means for positive and negative, when I try to find out the total sum of the errors, the same problem happens here also, that actually because due to high outliers, the sum may turn out to be 0, which we may give us a false notion that the expected value of the risk is 0, which is true coming out in the practical sense. But the outliers being very large, it may be a false notion. The other one is weighted linear loss function. If you see the part of the, in the negative part I have drawn it as red, positive part I have drawn is at blue. So, if you consider this dotted part, it means the negative part weights are more, while the positive part weights are less. That is why it is slanted. While if I consider the concept when the weights for the positive part is more and negative part is less, I have this part of the risk, which I am marking with different colors. So, the green one is for the part when negative part weights are more, positive part weights are less, for the delta loss, and still the linear weight combination of the loss, while the orange part which I have circled is for the case when the negative part weights are low and positive part weights are more. And this one is squared error loss, we have already seen, but squared error loss, as you see, has an advantage. In and around the 0, the concept of limit continuity concept problem is not there. The squared error concept, as I mentioned, minimizing that is akin and gives a huge set of information, huge idea that we are minimizing the variance also, which is one of the best thing to do. And obviously, with the sum of the errors concept is not there, mean absolute concept is not there, because you are squaring it. So, any positive and negative errors are squared up, but the outliers concept still remains. So, with this I will end this class and multiple linear regression, and we have the remaining class will be devoted, few more classes in the regression part would be for nonlinear regression, logit models and probit models. With that, I am sure there would be a lot of coverage in the second part of this course, second part being regression. First part we have tried our level best to cover all the models in forecasting as far as possible, and the remaining few lectures. So, if it is 43rd and we have another 2 lectures to complete regression, by 46th or 47th lecture we should start the time series model, which means from 46th, 47th to the 60th lecture, each being half an hour, we will cover the concepts of time series model. So, this small part I wanted to give you. So, with this I will end this class. Have a nice day and thank you very much.